Wonderful. Thank you so much. Hi, everybody. It's great to be there virtually. I am teaching this semester for the first time, which is why I couldn't be there in person with you all, but it's a pleasure to visit you all virtually, and I'm looking forward to our chats later. So I'm going to be talking to you about matter and strong gravity and using spectral timing analysis of black holes and neutron stars. I'm going to start out with oh no, it never likes when I push the button. There we go. I'm going to start out with a very broad introduction. This will be review for most of you, but people love hearing stuff they already know, so that's fine. And there's some pretty pictures. We'll talk about compact objects and X-ray binaries. And then I'll briefly go over the basic tools that we have for learning things about X-ray binaries, namely timing and spectroscopy. I have a few Q&A times scattered throughout because I know with the virtual talks, sometimes that can be a little easier. We don't have to use them and we can save them for the end if you like. For those of you joining virtually, I can't see the chat when I have my screens open. So if you could unmute, that is most helpful to me. Then we will talk about the signal that's nearest and dearest to my heart, quasi-periodic oscillations or QPOs. And then if we have some time, we'll talk a bit about X-ray telescopes that I use. NICER is a current one. Strobex is planned for the future, we hope. And Stingray, which is an open source software project that I am one of the co-developers of. And then I have a slide at the end about mental well-being in academia. I've always had it in my seminars, but with COVID, it seems especially important to keep it in for now. So let's get started. We'll first talk about compact objects and low-mass X-ray binaries. So compact objects are the dense stellar remnants of massive stars after they have gone supernova. We primarily look at neutron stars and black holes. White dwarfs are also interesting, and there's also a ton of cool variability stuff, but that is not exactly my field. If you want to chat later, I'd love to. But I'm going to be talking about neutron stars and black holes today. So neutron stars have a radius of about 12 kilometers or 7.5 miles, but within that, they have a mass of like 1.5 times the mass of the sun. The density that they have is about 10 to the 14 grams per cubic centimeter, which is the density of an atomic nucleus. Since their density tends to striate, they are more dense than an atomic nucleus at the core, and they are less dense at the outer edges. The surface acceleration due to gravity, because of this density and mass, is about 10 to the 12 meters per second squared, which, as you'll recall from intro astronomy, on the surface of the Earth, it's about 10 meters per second squared. And their magnetic fields of these neutron stars are 10 to the 8 to 10 to the 15 Gauss. So on the low end, this is still stronger than anything we've created on Earth. And they have spin frequencies up to hundreds of hertz. I did a quick calculation for how fast the high-speed blenders turn around, like what their rotations per minute are. And the fastest blender spins about 475 times per second. And the fastest neutron star spins about 700 times per second. So these neutron stars are spinning around faster than a blender. They have these different densities within. As I said, we have this outer crust of nuclei and electrons. This inner crust is where we start to get some superfluid neutrons, so we can learn more about ultra dense states of matter. And then at their cores, this is where we get some question marks because learning the equation of state for ultra dense matter is one of the open areas of neutron star astrophysics. For black holes, these are the ultra compact remnants of massive stars that were more than 20 times the mass of the sun. And the event horizon is about 15 kilometers for a 10 solar mass black hole. Here we have a plot of the black holes that have been discovered. It might be a bit dark on your display, sorry about that. The electromagnetically discovered black holes are in purple here. And then the ones discovered by Virgo are now all in blue. So this plot has expanded quite a bit in the last few years. And we see that most of the electromagnetically discovered black holes, nearly all of which are X-ray binaries, are all tending to be on the lower mass range of black hole masses. And the LIGO ones that we're seeing tend to be higher mass. This is likely an observation bias, not anything intrinsic. So this is the basic rundowns of black holes and neutron stars. And when I'm studying them, I look for them in low mass X-ray binaries. So as the name suggests, a low mass X-ray binary is a system in which we have a stellar mass black hole or neutron star and a low mass star like our sun. And they orbit a common center of mass. The companion star is overflowing its Roche lobe, and so its matter is more gravitationally attracted to the compact object than it is to its own star. As it flows towards this, though, towards the compact object, it has angular momentum, so it can't just fall straight down, and instead it all swirls around together and forms an accretion disk. This accretion disk is very, very hot. The viscous friction in it can give a black body spectrum with a peak in the X-rays. Because of this, we call these X-ray binaries. When we are analyzing the components of a Lowmass Xray binary, these are all point sources to us here on Earth. So imaging doesn't really get you very far. We use spectroscopy to kind of take roll call and see what physical components are present. So we also have this hot inner flow or corona. This is a hot, fluffy cloud of electrons, the geometry of which is debated and could be different for different systems. This has a Comptonized spectrum or a power law spectrum at higher energies. We also have a black body, a multicolored black body from the accretion disk. And then we have this reflection component. And this is where we have photons from this Comptonized region that are being absorbed and re-emitted by the black body before they reach the observer. You can kind of think of it like if you have a flashlight that you are shining yourself, and then you have a wall and you'd like to know a bit about the wall. If you shine your flashlight off of the wall and then it reaches you, you get to see some of the features of the wall, like if it's bumpy or shiny or matte and things like that. So in this way, we can use the information in the reflection component to learn a bit about the material and the geometry of the black body and the corona. So this is one way we have to study what components are present, but spectroscopy tends to only look at kind of large scale time averaged properties of the system. However, we also know from timing observations that these systems are dynamic on sub-second timescales. They show variability from a few hundred seconds to many hundreds of hertz. So sorry, from a few seconds to many hundreds of hertz. And we can analyze these with different timing techniques. However, traditional timing does not have too much energy resolution. So in short, the way that I analyze these systems is looking at the timing and spectroscopy information together in this region that we call spectral timing to learn more about what these different components are of the X-ray binary and how they're varying on very short timescales. So now we'll talk a bit more about those two analysis techniques in general. I'm going to let my dog out of my office 1 second. She doesn't like that I'm talking. Okay, go on. She finds it very rude that I talk about astrophysics during her nap time. Okay, timing and spectroscopy. So as I said, X-ray binaries are too small and too far away for imaging. If you do a back of the envelope calculation, this would be like trying to image a human hair on the surface of Mars at closest approach. So this is roughly like pico arc second resolution, which is not something we can do with X-rays. However, the physical processes that are present in these systems have these characteristic energy distributions, and so we can use spectroscopy to determine what's there. The accretion disk shown in blue here is this black body, or really a multicolor black body, because each different annulus of the accretion disk has a slightly different temperature, so they all contribute a little bit to the total black body. We also have this inverse Compton upscattering component due to the corona or hot inner accretion flow. And then this reflection component, we have a strong iron K alpha line, which I'll talk about in a second. We have this strong fluorescence line at 6.4 keV. And then we also get deviations from a power law up at higher energies. So when we are looking at this iron K alpha line in particular, looking at the shape of this can tell us a lot more about like what is happening within the accretion disk and what the relative geometries are of the incident light source, so this corona, and the accretion disk in relation to us as the observer. So with just Newtonian physics being taken into account, we would have two peaks in our iron K alpha line, one from the approaching side of the disk and one from the receding side of the accretion disk. Then with special relativistic effects in there, we have transverse Doppler shift and beaming. And so the blue shifted side of the line is a lot stronger and the red shifted side is a bit less. Then if we add in general relativistic gravitational redshifting, this entire thing is sitting very close to the compact object, so it's in a gravitational potential well. So the entire thing gets shifted down to the red a little bit. And then all of these factors, Newtonian, special relativistic, and general relativistic, are for each different ring of our accretion disk. And so when we smear them all together, we get this line profile. And so doing high resolution spectroscopy of the line profile of this iron K alpha emission feature can tell us quite a bit about, again, this geometry of the corona, the disk, how close they are to each other, and how they are relative to us. When we're looking at spectra, these are not constant over time for X-ray binaries. And so we can in some sense treat these as proxies for the accretion state. These timescales vary over like weeks to months or so, and then something can be not emitting much X-rays at all for many years. So we have this soft spectrum, which is when we have a very strong accretion disk emission and not very much at all in the Comptonized component. And then we have this harder spectrum where we have very strong Comptonized emission. So if we take a look at some artist impressions of what might be happening here, in a hard state, we expect to see a very, very bright corona or hot inner flow area. And the accretion disk is present, but it's not shining very brightly in the X-rays. And in converse, when we have a soft spectrum, the disk is very, very bright, but if there is a corona, it is not shining very brightly, at least to us. These systems together, the spectrum will change in what we call outburst over many weeks to many months. However, there are more interesting changes happening on even shorter timescales when the source is switching between having this hard corona-dominated emission and this soft disk-dominated emission. And this is what I like to look at more specifically in my research. So to do this, we use Fourier transforms because we're looking at very rapid sub-second variability. So the shorter 1 minute variability, we study the time domain, which is the red curve here, in the frequency domain. So to do this with the Fourier transform, we're breaking down our light curve into the component sine waves and then taking the amplitude of the sines of each frequency involved. This GIF is on Wikipedia if you want to watch it again at your own pace. I'll let it play through once more. So we have some light curve, there is some variability in there. And as we then, in some sense, what's happening behind the scenes is we are fitting a bunch of different sine waves to our light curve and saying, okay, how strong does the amplitude of this sine wave have to be to recreate the light curve well? We say, okay, there's a lot of variability at this low frequency, and there's not much variability at this high frequency to reproduce our light curve. So in this way, the amplitude or peaks in this frequency domain give us information about the time domain. And we do this when we're applying this to our data. We're not just looking at the Fourier transform all in one go, but we're breaking up our light curve into equal chunks and averaging our Fourier transforms together. Fourier transform squared is called the power spectrum or power density spectrum or periodogram. And so when we're doing this, we are taking our light curve and we're learning about things in the frequency domain because X-ray variability is very, very difficult to see by eye. So I want to just note here that the frequency along the x-axis in these plots is the Fourier frequency of variability in the time domain. It is not anything about the photon frequency. So the reason we do this is because X-ray variability is hard to see by eye. So in these two light curves, these are both of accreting black holes, one of which has a 0.5 Hertz signal. So there should be 5 cycles of a signal in the light curve I've given here. They're both 10 seconds long, and they have similar counts per second. And so well, one of these has a signal and one of these is just a bunch of noise that happens to look vaguely correlated for the time that I'm showing here. So I would like for you all to think for yourselves and then raise your hands. Do you think that the signal is in the left or the right? So can I have a show of hands for who thinks the signal is in the left side? And who thinks the signal is in the right side? A lot of people didn't vote. That's okay. You can think for yourself. So the signal is in the right side. So you can tell the reason why we have to do this Fourier analysis is because our eyes really want to pick out patterns, but the patterns aren't always actually there. So I should note that when I'm showing the power spectra down here, it's not just for the short segment that I'm showing here. I zoomed in so you could actually see the period of the signal, but it's for many signals averaged together. So this is why we have to turn to the Fourier domain and look at power density spectra or periodograms to look at these rapid signals that are coming from X-ray binaries. So this is the brief overview of the introduction. These signals are quasi-periodic oscillations. We'll talk about them a lot more, but I wanted to give a moment to pause for any questions so far.
I have a question here. So about the power spectrum that you just showed, both of them seems to have a rising power at the. So can we go to the previous one? Yeah. So both of them seem to have a rising power at about 10. Is that weird? Yeah, is that
it is.
Is that due to instrument or is due to something?
That is due to counting statistics. That's the Poisson counting noise level that has not been subtracted from these light curves. And so when you're plotting them as power times frequency, you get this sharp line at the higher frequencies if you don't subtract off your Poisson noise. Poisson noise is because with X-ray astronomy, we are counting individual photons. And so you have to get rid of the Poisson noise from your power spectrum if you want to see primarily the signal. We'll also talk a little bit about this like lump of noise that they all have. Any more questions for now? Okay, so now we're going to talk about quasi-periodic oscillations or QPOs. So I have a very brief, kind of simplified way to think of these if you're not used to thinking about quasi-periodic signals in the frame of damped harmonic oscillators, because introphysics loves itself a damped harmonic oscillator. So if we start with a pure sine wave or cosine wave in this point, in the time, we've got the time domain along our on the left side, and then the corresponding power spectrum of the frequency domain along the right side. So a pure sine wave has this delta function in the frequency domain. And as we add an exponential damping term to this, so we are damping our amplitude in the time domain, this shortens and begins to broaden the peak that we have in the frequency domain. So if I do this a bit more, we damp it more strongly. I'm just putting some term there. If we damp it more and more strongly, we find that the stronger the damping in the time domain, this wider peak we have in the frequency domain. And the amplitude is because the power is being spread out over multiple frequency bands. We notice that you can also almost think of it as the damping term that we have here is kind of telling you a bit about how coherent the physical process causing this signal can be. So if we then take this kind of damped harmonic oscillator perspective, when we try to reapply it to astrophysics, we can ask ourselves, what is the cause of the oscillation in the first place? And then what is the cause of this damping or dissipation that is happening? And then of course, this is a very simple mathematical model to just get what the time series versus the frequency versus the power spectrum looks like. We can say, what else are we not accounting for here? So in astrophysics, the types of QPOs that we have generally are classified as high frequency and low frequency because we're very clever with names. High frequency QPOs are at hundreds of hertz in black holes, and they can get up to 1,000 hertz in neutron stars. And these are thought to be roughly hot blobs in Keplerian orbits at the inner edge of the accretion disk, because the frequency at which we see these is consistent with the frequency of a Keplerian orbit at the inner edge of the accretion disk. So we can see that in a power spectrum, high frequency QPOs tend to be very nice and sharp here, and then they're sitting on top of some noise and then a bunch of low frequency noise as well. Where low frequency QPOs, these are at about 0.1 to tens of hertz or so, and in neutron stars, they can get up to more of like multiple tens of hertz. We have a few here on the right. And so these are, this is the same source looking at two different types of QPOs at two different states that it has. And we see that they tend to still have this nice sharp peak, and they also tend to have a harmonic as well. And they can sit on top of different types of noise. So the models for low frequency QPOs, this is still something that's an active area of research, of course. We think that there could be something about processing of a corona or hot inner flow, which I will talk a lot more about in a few slides. It could also be due to some magnetic warps in the accretion disk that are supporting some quantizing thing and then slowly moving through the disk as the matter accretes, or having some intrinsic fluctuations in the disk that are being Compton upscattered. But so I want to talk briefly about this, like how these different noise profiles look underneath the QPOs, because it turns out that these spectral states I talked about before, where we have this kind of hard corona dominated state and this soft disk dominated state, the power spectrum of black holes also changes with the spectral state. So these are all of different sources, but kind of showing what a typical power spectrum might look like in that spectral state. So when we have a hard state, so we have a lot of componized emission, we have a lot of overall variability in our light curves, but there isn't much of a particular frequency that stands out among the others. There's just a lot of variability. And then as we're moving into this intermediate state, so the disk begins to get brighter, this is when we start to see one type of QPO. So this is when we have this overall noise, this overall variability, but there's a QPO that sticks out on top of it. Throughout this hard intermediate state, so as the corona is getting less bright and the disk is getting more bright, this overall noise profile, so the overall variability, is decreasing in amplitude, and our QPO likes to wiggle and walk around throughout time as the source is evolving through its states. We then have another type of QPO. Astronomers love to assign types to things. Of course, not everything fits the types. That's how it goes. As the disk is getting brighter and brighter, we find that this variability, this overall variability, is decreasing and decreasing until eventually, when we have kind of only the disk that is bright, the QPO is gone. And there's just there's just not much variability whatsoever in the light curve. It's a very still and quiet light curve. So this is really interesting because it's indicating to us at first glance that this QPO mechanism, the thing that's producing this oscillation, has to have both a corona and a disk component, because when we have just a bright corona or just a bright disk, we're not seeing the QPO. So let's talk a little bit more.
In terms of the time it takes to evolve through these states, how does it go? Is the intermediate part very fast compared?
It's weeks. Yeah, it's weeks through these states. It can spend some time in the hard state and quite a bit of time in the soft state. Through the intermediate state, it might take, I don't know, 2 or 3 weeks. The type where it shows this particular type B QPO is very fleeting. This can be just a couple days. But in general, you have enough time to like trigger your target of opportunity observation that you have, or to submit a DDT if something is going into the hard state and it looks like it's going to transition into the intermediate states, then you have enough time to submit a DDT. One of the jokes my PhD advisor made is that you can also see a lot of this kind of general variability in AGN, but stellar mass black holes go through these spectral transitions and vary on timescales shorter than that of a PhD. So you can actually study multiple sources.
Right. Thanks.
Yeah, of course. So let's talk a bit more about this QPO mechanism and how it seems to require both a quantizing component and a disk component. So one of the theories that could possibly be causing the QPOs is lens-of-tearing precession. Traditional kind of classic lens-of-tearing precession is where you have a test particle in orbit around a spinning black hole, and the axis of the spin axis of the black hole and the axis of orbit for the test particle are misaligned. And so the plane of orbit of the test particle is precessing around the black hole like a top. So that's what this GIF here is showing. And some early work in the late 90s was showing that the frequency of this nodal procession of this plane processing around the black hole, this frequency is kind of close to what the frequency of these low frequency QPOs could be. But the low frequency QPOs were a little bit lower than that. So then later work was showing that you could instead have not just one test particle processing around the black hole, but you could have your kind of entire hot inner flow or quantizing region. If you could get that to process, then you could reproduce this low frequency QPO that you see. So in this kind of simulation showing here, we have our accretion disk is in the gray and the rainbow. And then this inner area, our quantizing region is more of like a compact torus that is this, it's still quantizing emitting, but it's not this fluffy corona. It's more of a coherent shape. And you can get a bend or break in your accretion disk, and it can process around the spin axis of the black hole. The color patterns here are showing the Doppler boosted and deboosted sides of the accretion disk, as we have the approaching and receding sides. I tried to use magnetic field terminology to help convey that. And so this is a cool idea, but then there was a lot of thought about whether this is like, can you actually get the procession, and can this actually happen? Like, it's nice that the numbers kind of line up that you could get this, but like, can a quantizing flow really break from the disk and do this? And so there has been some nice general relativistic magnetohydrodynamical simulations to show that indeed, if you put the procession in, like if you make them misaligned, that it can process all the way around, and you can keep your quantizing area coherent enough to process multiple times. So what we're showing here is how you can have this quantizing region that is supporting like a taller scale height, almost jet-like emitting region. And that if you put in the procession in the first place, it can continue this procession and it can wobble around your spin axis of the black hole. So there's some really beautiful MHD work by Sasha Tchaikovskoy, Kushik Chatterjee, Matthew Liska, and Sarah Markoff, showing a lot of cool simulations with different starting conditions of, if you put the procession in, will it last? If you don't put the procession in, can you get the break? These kinds of things. So this is something that only recently significant theory and computation time have been allowing us to explore more in depth. One of the tricky things is that the signals that we see from the black holes, these QPOs are stable for like many days to weeks, but simulating more than a couple seconds on compute clusters takes a rather ungodly amount of time. So we're getting there slowly. It's very exciting. So
can I ask a question?
Yes.
I thought that I don't know if these QPOs or the other ones, but that they were moving in frequency a little bit sometimes. Is that?
Yes.
Is this something that it can be explained through? I don't even know what's the status of that, but I remember hearing.
Yeah, so this is something that is being worked on like as we speak, I believe. Some of the arguments for this involve a truncated accretion disk, where as the disk is getting brighter, the inner disk region is moving in closer. And so you're kind of pushing your quantizing region smaller and then moving it up. And so as you're changing the size and scale of your quantizing region, this could change the frequency of the procession. And I don't recall exactly what the thought is for if there's no disk truncation. I don't know exactly how you can get this changing frequency for the type C QPOs.
Because
yeah.
they are, this is a stable phenomenology, and many of these examples show this motion of the frequencies. Is that true?
Yes. Yes, many of the examples, nearly every black hole shows for this QPO that's sitting on top of all that noise in the hard intermediate state, that can wander in frequency quite a bit. The one that's on only a little bit of noise when the disk is quite bright, this does not really wander in frequency at all.
And does the frequency change, is the frequency change correlated with the fitted parameters of the disk from the thermal part? So does it agree with this model in which the disk comes in, gets a little warmer?
It does generally agree with that, yes. But there's of course other evidence that we don't have a truncated disk at all. So then this kind of throws a wrench into that whole thing.
What's the time scale of the frequency evolution?
The frequency evolution is over a period of days. So for, let's see, let me go back to this slide. So you can start with something, this is at like 0.5 hertz or something, and you can get up to like 10 hertz over here for your fundamental. And this span might be a week and a half or so, like ballpark, like multiple days, but not multiple weeks. Of course, every source is slightly different. So the moment you try to put a firm limit on it, something comes along and breaks it. But so these QPOs that are sitting on top of this large lump of noise, we find that this noise is associated with, it is associated with the corona, but it is being produced by a soft spectral component. So it is disk related, even though it is only really present when you have a strong corona. So there are some models about if you have propagating fluctuations in your accretion disk that are then moving through your disk and then up into your coronal quantizing flow. There's a lot of nice work about that being done by Adam Ingram and Gulo Mastroserio. I'm happy to give those references later if you'd like. So yeah. So there's some theoretical work being done that is very cool and coming along. And as an observer, I would like to test these models. And say if this lensitarian procession thing is happening, or something similar to it, some kind of geometric change is happening, we expect to see a changing energy spectrum on the sub-QPO timescale. So we expect to see an overall change in normalization because the solid angle of the quantizing component is changing with respect to the observer. We expect to see an apparent change in the black body, not because the disk is actually heating and cooling, but because you are preferentially illuminating the blue shifted and red shifted sides of the accretion disk in a rather dramatic way. So you are seeing a more blue shifted disk and then a more red shifted disk. And also we expect to see a changing iron line profile. So as I said earlier, this iron line is because we have emission from this quantizing region that is being absorbed and re-emitted by our disk. And so as you're illuminating the red and blue shifted sides of the disk, you would also expect to see changes in either the iron line centroid energies, if not also just the overall normalization of it from looking at the blue and red shifted sides. So by looking at this changing energy spectrum on a QPO timescale, we want to determine this low frequency QPO emission mechanism. And then as we were just talking about, these different QPO types seem to switch from one thing to another, but we don't know if the mechanisms are strongly related. So we want to know if there are different mechanisms for these different types, or if it's the same mechanism that is just transferring into a slightly different region of the physical space or the parameter space. Because lensitarian procession isn't the only model, but it is a really cool one currently, and we'd like to test it. So to do this, we use phase resolve spectroscopy. Now, phase resolve spectroscopy of periodic signals like a pulsar is nice and straightforward. You can fold your light curve at the pulse period, and the signal stacks nicely in the time domain. And then once you have that, you have the pulse with the full energy resolution of your detector, and you can take your slices in the time domain of your stacked light curve, and then you have your spectra. To do this, you also not only need to have an exactly periodic signal, but you have to know the ephemeris of your source. So you have to have the exact orbital solution of your source, its companion, and its relation to us here in the solar system, which is not known for some of the new transients. And also there are some neutron stars that have a changing ephemeris. Either they're a transitional pulsar or they have a high mass star, and things tend to change. So to do this with quasi-periodic signals, we needed an entirely new analysis approach. They are not coherent enough to fold our light curve in the time domain. If you recall the damped harmonic oscillators from the very beginning, if you try to fold this too much beyond just that little bit that it's coherent, it starts to wash out and you are decreasing your signal to noise. So the signal will just smear out. So we have to average our signals together in the frequency domain, because we know from looking at power spectra that our signals stack up very nicely on top of each other in the frequency domain. It also so happens that our method for doing this, which was one of the first papers of my PhD, the ephemeris of the source is not needed. So we can also apply this to pulsars where we don't know the exact orbital solution of the source, or if it has a changing orbital solution, which is pretty convenient. So in kind of a tongue-in-cheek way, we used to say that sometimes you have a problem you want to solve. You want to do this phase resolved spectroscopy of this quasi-periodic signal. And an exact way of doing that can be pretty hard, might only work for some sources. However, you are not always required to go through the wall. You may also sometimes go around the wall or over the wall. And so if you Fourier transform your problem into the frequency domain, then your transform problem could be quite easy to solve. So stacking your signals in the frequency domain. And then once you have your solution there, then you can inverse Fourier transform it to a cross correlation function and get your solution in the time domain. So this is kind of what we did. So here is a more recent example of this work. This is a dynamical power spectrum. So we have our frequency, the former x-axis is along the y-axis here. And then our elapsed time is stepping along in the x-axis. And the color amplitude is showing the amplitude of the power spectrum. So the light yellow is where you would have like a peak in your power spectrum, and the dark parts is where it would be very low amplitude in your power spectrum. So by looking at this, we can see how these QPO frequencies are changing in time, because as we were just talking about, they definitely change in time. So we have this broadband or band limited noise, this kind of corona disk interaction. We have a nice little low frequency QPO ticking along here. A lot of these sudden jumps, especially these ones, are due to orbital gaps from the spacecraft. They are not intrinsically significant jumps like that. And then we have our little harmonic ticking along. And one thing we were interested to learn is there was this kind of dark part where we expected to see the type B QPO, but this was kind of a lower amplitude source. And so we wanted to see if something was hiding out in there. And indeed it was. We had to average our signals, all of our segments together for it to be visible, but we found that actually this type B, this QPO is likely present in a lot more sources. It just isn't immediately visible to you, which also indicates that the mechanism that produces this QPO is happening much more frequently than we initially thought it was. So in our more traditional power spectrum, we have our QPO here, very nice, a little harmonic, and then our broadband noise from the disk. So as we start to do some phase resolved spectroscopy of this little QPO right here, what I'm showing here is a ratio of the phase spectrum to the mean spectrum. So you can see the relative differences. We have our X-ray energy along this axis. So this helps us to start to look at how the spectral components are varying with QPO phase. And one thing you'll notice right away is that we have this increase.
Can you explain it again what you're doing, because I missed it and it looks cool, but I didn't understand. So you go back to the previous one.
This is just showing you what the QPO is.
Yeah, but then how are you getting your frequencies? Your frequency in photon frequency spectra, I guess, is the next plot. What are you doing? You're binning, you're stacking. I didn't get this.
No, I didn't explain the details of the technique because it is only interesting to a small subset of people I have found in past talks. I'd be happy to chat with you in more detail if you would like to in a later meeting. We are using the cross spectrum and the cross correlation function to get the relative deviations with energy with respect to a reference light curve of the QPO.
But then when you're
correct.
showing
I did just gloss over it.
When you show this movie now, it corresponds to different times.
Yeah, so each
that plot.
No, not in that plot.
This
is new. It is of the same signal, but this is new.
Okay.
So this is looking at, so each frame here is a different phase of the QPO. And we can see how there is a high energy kind of Comptonizing variation and a little bit of a soft disk variation, but they're out of phase with each other. So this has a slight phase lag, which gives it the kind of doing the wave appearance that the spectrum has. We find that this phase lag is present for most QPOs, and you can actually start to, there is a correlation between the phase, the amplitude of the phase lag and the inclination of the source, which is pretty interesting. I can give you a paper about that later if you like. And so the direction of this phase lag, where we first have this variability in the Comptonizing, and then we have the variability in the disk, this can start to inform us about how the physical components themselves are actually varying to produce not only the QPO, but this lag in the phase of hard and then soft. So with a previous paper that I did, we found, given that QPO and phase lag, that we had this kind of tall jet-like emitting region that was wobbling around, giving our QPO. But for this one that I'm showing here, this lag sign is opposite. So it's comptonizing and then soft, and the binary system has a different inclination to us. And so based on all of these things and some other information, we've inferred that this source likely has a smaller scale height emitting region. So if we have this comptonizing region is this gray torus here, and the disk is this orange part, we have this very small, compact scale height emitting region. So we are first seeing a maximum in the comptonizing component as it points towards us, and then 25% of a phase later, as it's preferentially illuminating the blue shifted side of the disk, then we're seeing the maximum in the disk side.
Sorry, if I were to just kind of in a dumb way take the hard photons and the soft photons and do a cross correlation analysis, would I see this?
You would see a little bit of it, but you wouldn't be able to fit detailed energy spectra to it. Yeah.
Okay.
Yeah, so the way that we're doing it, we can fit detailed spectral models, so we can actually see like variations in other components as well. But yeah, so that there were indications that something like this was happening before we were doing this type of analysis. Yeah. Oh yeah.
Just to clarify, so in this movie that you show here, so is this only the low frequency QPO, or it has both low frequency and high frequency QPO?
This is just looking at the low frequency QPO, but there is no high frequency QPO in this source. The harmonic is included as well, though. So it's got the broadband noise, the low frequency QPO, and the harmonic. There is no high frequency QPO in this source, unfortunately. Yeah.
And if we do make a similar movie for high frequency QPO, do we see anything like this, or?
Yeah, so we have not been able to do that for a black hole high frequency QPO because they are very hard to find, and they tend to be very weak. The high frequency QPOs in neutron stars are much stronger. I have some bonus slides that I can show you later. The hard thing there is to get enough time resolution within one oscillation, because these oscillations are like 800 or 900 hertz. And so even your fastest time resolution can only give you like 10 time bins across that. But we do see phase lags there as well. Yeah.
The phase lag on the video, is there a way to relate that to like wave propagation speeds in the disk? If you like correspond to energy bins to radii?
Yes, this is involved in some of the models done by Adam Ingram. Adam Ingram and Lowmass Xray have been building some of the models that we can use to fit these, to take the energy and timing information into account together, because previously you could either just fit a timing model or just fit a broadband spectral model. So yes, there's some initial work being done with this, but having a propagation speed through the disk does not explain the QPO. It only explains the kind of lower humped frequency broadband noise. So as we were hinting at with the last one, there seems to be this relation between this comptonizing region and the QPOs. And we have found more evidence recently that these low frequency QPOs and the transitions between them are linked to the radio jets that these sources have, and having discrete ejecta in our radio jets. So we have this transition between types of QPOs. So here we have turquoise and purple, indicating two different types of QPOs in the source. These correlate with the radio jet turning off in the red line and having discrete jet ejecta, which is happening in the blue line. This has been long suspected. There have been radio flares previously within like a day or so of the QPOs turning off in previous work, but it was with MaxiJ 1820 plus 070, which was a super, super bright source from a few years ago that was the subject of many multi-wavelength campaigns. We were actually able to get this correlated to within only a few hours. And so this was very interesting in that we could actually see that when the type B QPO here is turning off, this was when we had the start of a flare. So this is starting to relate, we think, whatever this QPO emission mechanism is with the jet launching and quenching mechanisms, which is super cool. So yeah, this QPO emission mechanism is closely related with the jet emission region. With one of my summer students, we tried to phase resolve this QPO that's indicated with the purple here. Unfortunately, it was too low amplitude for full phase resolve spectroscopy. But again, indicating that these QPOs are present more often than we think. You just have to look more deeply and average more data together to actually see them above the noise. But so to investigate this link between QPOs and jets a little bit more, we have two accepted JWST cycle 1 campaigns that I'm a co-I on. One of them is to improve timing calibrations with NIRCam to get clock accuracy down to about 40 milliseconds to correct for the mission clock drifts. Since it was not designed as a timing instrument, the clock up on the spacecraft has a drift from whatever the set one is down at the ground station, and it resets whenever it reconnects to the ground stations. And by carefully monitoring this, this can allow us to correct our spacecraft clock data more to more detail, which will then allow you to take the timestamps in your data, apply the corrections, and then do rapid IR timing observations. We also have a campaign with MIRI to do sub-second observations of a black hole in outburst in this intermediate state to try to catch this infrared variability of the jet launching, because these QPOs that we see are also visible in optical and infrared data as well at lower frequencies corresponding with the lower light energy. The PI for these proposals is Poshak Gandhi, and the co-PIs are Tom Macron and Aaron Shaw. It's very cool. I can't believe we got these in, but I'm excited that we'll get to investigate more of the QPOs relating to the jets with JWST coming up, hopefully soon.
Can I ask a sort of more general background question?
Yeah.
Before, so I remember that for low frequency QPOs from black holes, there was this correlation between the masses and the frequency of the QPOs. And this is why people were considering these models in which the QPOs arose in a particular region of the disk, very specifically related to X number of Schwarzschild radii, blah, blah, blah. But yeah. So if they wobble in frequency, then this has gone away, or what's?
Yeah,
so
that's largely gone away. That has largely gone away. That was present in some of the papers that I was reading during my PhD, but it was never something that we actively discussed. So my understanding is that it's not really an active consideration anymore. Okay. So I know we're almost up on time, but do we have any more questions for this bit? These next few things are very quick and I can skip them if we need to. I keep going? Okay. So now we'll talk briefly about NICER and Strobex. So this brief intro slide, the point of it is that X-rays cannot get through Earth's atmosphere. And so if we want to look at X-rays coming from space, we have to get above the atmosphere with satellites and put our telescopes on satellites. Unfortunately, this is quite expensive and takes a very long time, but when it happens, it's very cool and very worth it. One of the telescopes that I am using most is called NICER. NICER is attached to the International Space Station. It was launched in 2017. It is kind of an all-in-one X-ray timing instrument. It has better timing than RxTE and AstroSat, which were the previous best timing missions, with a CCD energy resolution of XMM Newton. And it has a very high throughput, so we can look at very bright transients within our galaxy. We are always looking at galactic sources for the most part. And one of the problems with the very sensitive X-ray telescopes that are intended to look for faint things in other galaxies means that when something stupidly bright is happening in our own galaxy, you cannot look at them with things like Chandra or XMM Newton, because it just overwhelms the detector and you don't get useful data. So NICER is able to stare at very, very bright sources. We've even had to turn off portions of the detector to read out the data in time in order to telemeter the information down in time, which is a very exciting problem to have when you have to shut off like 3/4 of your detector to actually see the photons. And NICER is able to do that, which is just fantastic and amazing. That's NICER right there. It's about 1 meter cube, so it's the size of your dishwasher. X-ray telescopes don't look like kind of standard optical or radio telescopes. This is kind of showing you how the photons come in. We have these concentric circles that do a single bounce. to focus the X-rays onto the back plane. So we have these 56 identical detectors, which is how we can just shut off parts of them and the rest of it works fine. And then we have our CCD chips along the back for the readout. So here we have a little video of NICER in action. So that's the back of the detector right now. And it's slewing around looking at stuff. You can see other things slewing around down here as well. There's the solar panels. Yep, and that's where the photons go in these little concentric circles. So NICER has very fast response time because it is intended to be looking at X-ray transients. The initial mission is to do a very detailed pulse timing and phase resolve spectroscopy of accreting neutron stars to help constrain the neutron star equation of state. But it's also been incredibly useful, kind of all sorts of galactic compact object X-ray studies, which is very cool. If you want to ask more about NICER during the discussion time, I'd be happy to chat your ear off about it. It's wonderful. We've now had 3 cycles of guest observing, and the 4th one will be coming up in probably 6 months or so. And they also are very friendly to DDT requests as well. Another telescope that I am on the steering committee for is Strobex. And this is a proposed probe class mission that we've put forward to the 2020 Decadal Survey. Probe class missions have a $1 billion cost cap for the entire development and 5-year nominal mission lifetime. And the components of Strobex are this wide field monitor to do kind of large, just general monitoring of the X-ray sky. This is very important because MAXI is already past its initial lifetime and SWIFT is getting quite old, and it would be a huge pity to lose an all-sky X-ray monitor. This X-ray concentrator array is basically like a super NICER, looking at 0.2 to 12 keV. And then we have these large area detector panels to look at the mid X-ray region. And these will also have very fast timing readout that will be wonderful for the QPO analysis that I do. So, Strobex is combining the strengths that we had of NICER and LOFT, which was a proposed X-ray mission to ESA that did not end up going through, but it had a couple of years of development, so we know a bit more about the technology and how it will work. All the components are already at a high technology readiness level, which is wonderful, and it has a highly modular design, which allows us to scale up or realistically scale down as budgets and space require. The science drivers for it are kind of all aspects of compact object studies, spin distributions of black holes, accretion disks, even looking at like gamma ray bursts, LIGO electromagnetic counterparts, tidal disruption events, and just new sources. You never know what you're going to find. So for my own research, having the sub-millisecond time resolution and the CCD energy resolution with soft X-ray coverage will help to resolve how these physical components vary that cause the QPO and where they're located. So you can disentangle the black body from the confinizing region. So Stingray Software, just one more minute. This is a open source timing and spectral timing software package that I am one of the co-developers of. It is AstroPi affiliated, and this is our docs website. .science is a valid domain name now. Stingray is a library of analysis tools, as you can import Stingray and do power spectra or cross correlation functions or things like that. Hendrix is a shell scripting interface that is specifically good for doing new star timing, and Dave is a graphical user interface. If you like to click buttons and kind of drag things around as you do your exploratory analysis. We have tutorials in Jupyter notebooks that not only explain how to do things in Stingray, but why you might want to make a power spectrum, for example. So they're great introductions for students. As usual, we are well documented with unit tests and kind of following the standard best practices for open source research software. We have a paper in AppJ and in JWST. We've had some great luck with Google Summer of Code students. Oh, there's something in the chat.
Mute yourself, if possible.
Yeah. My last slide is just, I've always kept this in about mental well-being in academia, but with COVID, it seems extremely important to put this in there. But overall, there is generally a mental health crisis in academics. Before COVID, about 1/3 of grad students met the criteria for depression, and I think COVID has exacerbated this quite a bit. And studies have found that gender minorities had much higher rates of problems than cis men. One of the things that is important to consider with all of this is that the work and organizational context, which includes your satisfaction with advising and your work environment and your colleagues, these are significant predictors of mental health. And I say this because this is something that individuals and institutions can actually make meaningful changes about. So I have a lot more statistics and tools and resources on my website, but overall, just please be aware, take care of yourself, and look out for your friends and colleagues. So that whiplash. In summary, Xray binaries are really awesome. They're one of the best tools that we have for studying matter in strong gravitational fields. And I use Xray spectral timing analysis to decipher the emission mechanisms for rapid variability. We find that these low frequency quasi-periodic oscillations could be due to this precessing hot inner flow or base of jet, and that these variability transitions are linked to discrete jet ejecta in the radio jets. NICER is a soft X-ray telescope on the International Space Station, and Strobex is a proposed large area X-ray observatory. And for Stingray, you can go and check out our docs online. And with that, thank you very much for inviting me.
Are there any questions here in the audience? Yes, Richie.
So I have a question. So in your one of your slides, you show that in your live fitting, you actually consider the gravitational redshift. I'm wondering, like, is that measurable, like from your these fitting procedures? And if we can get them gravitational redshifts, then we start to understand more about the system. For example, the mass or the equation of state.
Let me pull up that slide. So the gravitational redshift is one of the components that goes into these models. You can get approximately the mass from these models, but not to the precision that you would want for like measuring the equation of state, for example. Like you won't be able to get like less than 10% error to put meaningful constraints on the equation of state. You can tell if it's a neutron star versus a black hole. But yeah, in terms of the detailed model fitting, I don't think it is primarily the models that I've used are primarily designed for black holes that have only been recently extrapolated for use on neutron stars. So like Relzil, for example, yeah, that's recently been extrapolated for use on neutron stars, but there are still only some, for that particular model, which is the one that I've tried, there's still only some regimes in which case all of the assumptions of the model hold, so you can't use them in all of the states.
Is this line actually,
Sorry.
I was just going to say, is this line actually seen in neutron stars?
Yes, it is seen.
And
Renee Ludlam is doing some nice work with that.
And it's it has the same kind of shape characteristic of the.
Yep.
Okay, thank you.
Yeah, Renee Ludlam is doing some really nice work with that. If you want to look up more.
I just had a follow-up question. So is the mass a free parameter that you're fitting for when you're looking at to fit the line out there, or are you informing it?
You can let it be a free parameter, or you can fix it to 10 solar masses, which a lot of people do.
You don't have extra information from orbital dynamics or studying the companion.
Right. So typically we have a mass from orbital dynamics or something thereabouts. And so we would fix it to that, or we fix it to 10 solar masses, because it is not very sensitive to that. The other factors here, like the special relativity, and like the number, kind of the size of the disk, so like the number of annuli that you're adding together, these are a much stronger factor than the gravitational redshift.
Thanks.
Yep.
In terms of the modeling of the QPOs, are these frequencies, can you get the spin, for example, of the black hole, and what's, is there any?
Yeah.
What's the status of that, I guess?
So, yeah, there are some ways to try to find the spin of the black hole from measuring the QPO frequencies. There are a couple papers from the late 2000 aughts. Is that how you say that? Early 2010s, where if you have two types of low frequency QPOs and a high frequency QPO, and you assume that these are giving you, like the high frequency QPO is giving you the orbital frequency, and then one of these is giving you the nodal frequency, then you can try to plot them and say, then what would the spin of the black hole be to give me this? In general, the spins from the black hole, the spins gotten from the QPO measurements tend to give you low black hole spins, and the spins gotten from like looking at X-ray iron line spectroscopy, those tend to give you pretty high spins. And so one of the kind of open questions is, how do you reconcile the two? Is like it, because it doesn't seem very likely that we happen to be measuring all the high spin ones with spectroscopy, and we happen to be measuring all the low spin ones with timing. So there is some meshing that needs to happen there. But yes, they have gotten some spins from that are plausible.
And is there any system where you have a measurement of the spin with more than one way, maybe also with the spectra of the disk or something like that, right?
Yeah, so there's a talk by James Steiner that I'm trying to picture in my head right now. And he had a table of which sources we have which measurements for and which ones are in conflict. Basically, some of them are in conflict, but some of them are in somewhat of an agreement. And they're actively trying to reconcile these. So Jack Steiner's doing a lot of nice work about this right now.
Can I interject and add that there's a paper by Greg Salveson that analyzes both a K alpha iron line and SED fitting for spins in like 7 X-ray binaries or something like that.
That's right. Thank you for reminding me. That's right. That was a great paper. I'm sorry I forgot that.
What was
Thank
that
you.
paper? Sorry, can somebody?
Salveson.
Oh.
Do you remember what year it was?
No, because he sent it to me when it was first rejected, and then he revamped it. So I don't remember the year. But Matthias, you can just send me an email and I'll find the reference for you.
Thank you. I'll do that. Thanks.
All right, any more questions? On Zoom, I don't see anything. Okay, so if not, let's thank Abby again.
Thank you, everybody.